play from the start. Because the solution for one can be harnessed by others. Because clouds that compete can still connect. Red Hat, our code is open.
All right, if everyone's ready, let's get started. Welcome, everyone. My name is Andrew Brust, and this session is Analytics and AI with Azure Databricks. To some extent, that title is self-explanatory, but I'll just tell you, if we can cut through all the syllables, all the verbiage there, what we're going to do is spend some time learning about Azure Databricks, and because it is based on an open source technology called Apache Spark, we're going to learn an awful lot about Apache Spark at the same time. And in fact, those skills are portable across a number of other environments. Spark shows up again and again. We're going to be focusing on both the data analytics side of Spark and also the machine learning side of Spark. And I will presume no prior knowledge of machine learning. I'll try and take you through the basics of that as well. Maybe that's a little ambitious, but I hope to prove to you it's actually pretty reasonable. My firm, Blue Badge Insights, focuses on this area. We focus on data and analytics and business intelligence and artificial intelligence. And we do strategy and advisory work with companies in that space. That includes Microsoft, that includes companies like Cloudera. I also write about that space. As a blogger, as a journalist for ZDNet. I cover it as an independent analyst for a research firm called GigaOM, and I've been involved in the Microsoft ecosystem for a very, very long time, going back really to the mid-1990s. So all this stuff comes together in a way that I think makes sense for this event, and so without further ado, let's go ahead and drill down on the topics that we're going to cover today. So because Databricks is based on Apache Spark, that's where we're going to start. We're going to start with just some basics about Spark itself, what it is, what it does. Then we'll layer on the basics of Databricks, of the environment, the kind of mechanics of how you work in there. When you do work in Databricks, most of the stuff you're going to do is going to be in code. And most of that code is going to live in these things called notebooks. And we'll need to explore what notebooks are all about. So we'll do that. And then we'll go into several subject matter areas. We'll start with, what we call data lake analytics. That will include a look at how to work with Spark data frames, how to do data visualization, and how to do this all in the context of data files that may be living in Azure Blob Storage or in Azure Data Lake Storage. We'll see how to kind of string all those things together. Then we'll look at machine learning. And by the way, not just machine learning and predictive analytics itself, but also the operational aspects of that, ML Ops as it's called. And that will give us a chance to look not only at Spark's machine learning, but around this machine learning operations framework called ML Flow. We'll then move on into a more advanced data lake scenario that Databricks likes to call the data lake house. And that's where you do advanced stuff with data lake, but you end up getting some of the capabilities that you would have in a data warehouse. And that's where that name comes from. Now remember, this session is recorded. I'm not live. I'm talking to you from a couple weeks before you're seeing this. But I'm attending this session live the same way you are. And that means I can take your questions while the session is happening. And because of that, rather than having a dedicated Q&A section at the end, we're going to fill the whole 75 minutes with content so we can cover more. And I hope you agree that's the right decision. So let's kick things off with this Apache Spark backgrounder. And we won't have to lay out too much foundation because as we go through all the Databricks demos, that's really how you're going to learn about Spark in particular. But understand just the history of this thing. And you see the logo for it on the upper right-hand side of the slide there. And the thing about Spark is it's a big data framework. And originally, it was sort of a competitor to the more old school open source framework for working with big data, and that was called Apache Hadoop. The big difference between those two is that Hadoop was very oriented to putting intermediate results on disk. And when you're talking about huge volumes of data and analytics tasks that may run as batch jobs overnight, the latency that comes from that is not a huge deal. But if you're going to be doing interactive analytics, it is a big deal. And what Spark does is it moves that orientation from disk and takes it to bringing it in a world of in-memory computing. And that really makes things a lot snappier, a lot more interactive. It works better for BI-style queries and won't relegate you to these kind of overnight batch jobs. And although Spark was originally designed for doing big data analytics, it can actually take on a variety of workloads. And that is because in addition to the core Spark project itself, it contains several sub-projects, and we've listed them here. Spark SQL allows you to query the data that's in Spark using a dialect of SQL. And it actually allows you to manage SQL databases and tables as well. There's a component for streaming data called, logically enough, called Spark Streaming. There is a graph engine called GraphX, and there is the machine learning library, MLlib. So we're going to be looking mostly at the first one of these and the last one of these, Spark SQL and Spark MLlib. GraphX has not, really had a huge amount of adoption or following. Spark Streaming does, but it's really its own subject, and so we won't be covering it here. But what I will say is that everything you're going to learn about how to work with data frames and data in general in Spark and Databricks means that you'll be set for working with the streaming as well. And that's because Spark structured streaming works very hard to make streaming data behave and fit into the constructs of static data. So in fact, even though we won't be covering streaming directly, a lot of what you'll be learning here will be applicable to the streaming scenarios. That's really all we need to cover for Spark's basics, but now we need to talk about Databricks. So what's the difference? Well, Spark is really just a framework and APIs, right? Spark is a bunch of bits that you can download and you can install on your own compute cluster or even on a single machine. And then typically you might bring some Jupyter notebooks on there to get your work done, and you'll string in your own cron job manager to run compute jobs on a scheduled basis. It's a lot of do-it-yourself involved there. Databricks is a fully managed environment that gives you notebooks built in. It also allows you to define multiple clusters, and it will handle the life cycles of those clusters for you. It has its own notebooks and its own job scheduling facility. So everything you need is in there. Plus, you get a commercial version of the Spark engine, which is called the Databricks Runtime. And Databricks says that that engine is actually 7 to 8 times faster than the open source one. And please understand that the founders of Databricks, the company, were also the creators of Apache Spark. So this is not some unauthorized commercial version. This is actually a souped up version invented by the same people that invented the open source code on which it's based. So when you're going to work with Azure Databricks, the first thing you need to do is provision a workspace. And the workspace is necessary. It's kind of a container for all your work, for your notebooks, for your defined jobs, and for your databases. And even though you need clusters for anything to run, the workspace allows you to define and manage all of these entities in effect in an offline way, so that you don't need a cluster in order to persist those things. The cluster will be brought up, or multiple clusters will be brought up on a just-in-time basis to go ahead and execute your jobs or run your notebooks or what have you. You'll notice at the bottom of the slide here that there's a couple of different pricing tiers for Spark workspaces. There's a standard and a premium. Really, the big difference there is around security, granular security. You get role-based access controls with premium. You really don't get that with standard. You can still have multiple users with standard, but the permissions don't end up being as granular. There is also a trial workspace, and that is an option to check out if you want to work in a more educational environment and not worry about actually having to pay while you're first figuring things out. Now, once the workspace is set up and you're in it, then you need to define clusters. So these cluster definitions will sit there idle until a cluster is needed, and then Spark will spin it up. And here too you have choices. Here again, there is a standard and something else. So the standard cluster is great for single users. Even if there's going to be lots of parallel processing going on, that's the right choice for single users. The high concurrency type of cluster, on the other hand, is great if you're going to have multiple concurrent users all using the same cluster. Notice also, if I can wiggle the mouse over here, that you can set a timeout, an inactivity timeout. And this is great. That means basically if the cluster spins up and then you stop using it, that after a certain amount of time, it'll automatically spin down. This is great for anyone who has had the experience of setting up cloud infrastructure and forgetting that it's up and running and then getting shocked by the bill when they realize they never took it down. Now, if you're okay with things persisting longer than that, you can define a pool. And the pool will keep some nodes kind of warm and ready so that when it comes time to spin up a cluster, that can happen much more quickly. Notice that the cluster itself can auto scale. You can specify a minimum number of workers and a maximum number of workers, and then Databricks will make the decision of how many nodes should be deployed, and you can make sure that it won't go over that certain threshold. So lots of stuff you can configure here. You can pick your particular node types, which really just correspond to virtual machine types with different profiles for the number of compute cores and the speed of those cores, and also the amount of memory on the server. All right, so we need to talk about some basic Databricks constructs next. And we've already talked about the workspace that appears on the top of this slide. And we just talked about, excuse me, the clusters, which you see sort of towards the middle. A lot of the work that you're going to do with data in Databricks is going to be in code and in memory, but it is possible, and in many cases desirable, to persist your data frames out as physical tables in a physical database. And so Databricks will manage those databases and tables for you. You'll need to spin up a cluster, do anything with them, but the nice thing is when a cluster goes away and a new one comes back, you get all your kind of database state back automatically. You don't have to rebuild that. As I mentioned, Databricks has its own jobs facility built in. It also has made machine learning models a first-class object, and that's because it now includes MLflow's model catalog, model repository, and we'll take a look at that towards the end. But that's why you'll see in the main menu that there's an option for models. And then finally, because Databricks is a standalone, self-contained environment for running Apache Spark, it also has its own file system. That's called the Databricks File System, or DBFS. And that's a great place for kind of local storage, local to the cluster. But also, it ends up having some virtual directories that have some very useful sample data sets in them. And as you'll see in our first demo, as a matter of fact, you can take a container from Azure Blob Storage or Azure Data Lake Storage, and you can mount that container to show up as a folder in the Databricks file system. And then it's as if that data, even though it's in cloud storage, it's as if it's stored in the Databricks cluster's own storage. So we'll see a lot of this at work. In order for us to see that at work, though, we're going to have to open up some notebooks and write some code. So let's talk about the mechanics of that before we hit our first demo. So what is a notebook? Well, I like to think of it as a wiki based on Markdown, except within all of that Markdown, you can have regions or cells those regions can have code, and that code can be executed right inside of the notebook. And the output that it creates will be rendered in the notebook as well. Now, Spark is very often paired with an open source notebook facility called Jupyter Notebooks. But in the world of Databricks, you won't need Jupyter. Databricks has its own notebook format, its own notebook facility. But importantly, Jupyter Notebooks can be imported in. So you are able to bring your Jupyter Notebook IP into Databricks, but the formats are a little different. Now, each format has its own default programming language. But as it turns out, at the cell level, you can write code in any supported language as long as you put a little directive up at the top. And that directive is called a magic. Magics are preceded by a %sign. And so maybe you have a notebook based on the Scala programming language, but you want to have Python in a particular cell. Well, then you go ahead and you just put %Python at the top of that cell. And then from there, it becomes legal to supply Python code. Some other magics are noted here, and you can even have magics for things like file system commands. So it's not just about programming languages per se. Now, what are the particular languages that can be in a notebook? Well, they're kind of listed here. So we've already talked about Python, and that really is going to be the most common one at this point. That's why we've bolded the text. Spark SQL, which is Spark's dialect of SQL, can be used as the default language. So even though we don't think of SQL as a procedural programming language, you can still have SQL notebooks. Scala is a Java virtual machine-based language, and it is the native language of Spark and thus of Databricks. So that's another option, although it's less popular than it once was. And speaking of a little less popular, the R language, which used to be really a behemoth in the world of machine learning, it's still present. It's a little less popular than it was, but that's an option as well. So these are the 4 programming languages you can use, and you will see in our demos really a mixture of the first 3. First couple of notebooks will be Scala. The second couple will be Python, and we'll have some, at the cell level, we'll have some SQL as well. All right, that's really it for the basics. Now we move on into these subject matter areas. So we're going to start with Data Lake. A little bit more fundamentals to cover, and then we'll get right into the demos. And so we already mentioned Spark SQL. If you've ever worked with Hadoop and something called Apache Hive, it is actually the same kind of table infrastructure, and it is the same dialect of SQL that you can use when you do the queries. There's also a JDBC driver for Spark SQL, so that if you want, the data in those tables and in those databases can be queried from external BI tools. That can work as well. As you'll see in the demos, there's a very tight relationship between Spark SQL on the one hand and the data frame API that you would use in a language like Python on the other. And in fact, there's a somewhat trivial demo here at the bottom of this slide where you have an API line of code for caching a table, and then you have the Spark SQL equivalent. So most things you can do in Spark SQL, you can also do in code. And in fact, in code, you can embed Spark SQL commands as strings, and you can run them that way as well. So what about these things called data frames? Well, they're containers for rows and columns. They're a lot like data tables in ADO.NET for those of you, and I assume there are a lot of you with a .NET background. So that's worth knowing right there. The magic thing about data frames is that no matter what sort of domain within Spark and Databricks that you're working in, whether it's analysis or data engineering, which is kind of a fancy way of saying ETL, or you're doing streaming data, or you're doing machine learning, data frames are just sort of the bread and butter of all of them. And that also means you can mix workloads, right? You can do a bunch of analytics and data engineering, and then with the data frame that results, you can then go ahead and train a machine learning model from it. So unlike Hadoop, where each of these things required a separate kind of framework and engine, in the world of Spark and in the world of Databricks, you can mix and match all of these workloads. That's kind of a big deal. There are lots of advanced functions that return data frames, and that includes, for example, if you run a bunch of predictions through a machine learning model, you'll get those predictions back in the form of a data frame as well. Once you've populated a data frame, if you want, you can save it as sort of a temp table or a view, and then you can query it with Spark SQL. And again, that's because there's this fluidity and kind of compatibility where pretty much anything you do with Spark SQL, you can also do with the data frame and vice versa. Anyway, the line of code to do that appears at the bottom of this slide. It's dataframe.create or replace temp view, and then you put the name of the view as the parameter, and let's suppose we called that view my view. Well, then we could do a select star from my view pretty much right after we created the temp table that's based on it. Now let's look at a little bit more code in the slides before we hit our first notebook. How is it that you populate a data frame? Well, the most common way is that you're going to read data either out of a database or out of a file or a set of files. So spark.read.format, then you specify what format it is you're reading. It could be CSV or Parquet. It could be this thing called Delta that we'll look at the end of the session. You can specify a bunch of options. Then you say .load and you give it a pointer to a file or to a folder. All right, options are there for doing things that are context specific to the format. So in the case of CSV files, you may want to specify whether the first row is a header row, and you may want to ask Spark to infer the schema for you. In the case of a database, you might want to supply credentials, of course. A simpler way of doing this, instead of saying .format and then putting the format in as a string, there are named methods that are format specific. So you can actually say spark.read.csv and then pass the file spec or folder spec directly, and then you don't need the .load. Saving is kind of the same thing. There's a symmetry there. So once the data frame is populated, it's pretty easy to say dataframe.write and then either .format or one of the named methods like Parquet or CSV to go ahead and save it out. So there's an explicit save method if you're doing format as a string, and if you're doing the named method, then it's implied. And this is a nice thing. There's lots of other options. You'll see that we have the option to overwrite or to append. You'll see that in our demos. Now, what if you actually want to create a table in your Spark SQL database? Well, that's not hard. You just do save as table instead of save. And that really brings things out nicely. All right, guess what? It's time for our first couple of demos. So the first one's going to be very simple, just to give you the mechanics of mounting a blob storage container. Spinning that up, reading some data out of it, in this case in JSON format, and doing a SQL select against it. And then we'll move over to Azure Data Lake storage and a much bigger volume of data, and you'll be able to see how things work in that non-trivial environment as well. So I'm going to move over to our first notebook, and this notebook itself is very simple. There's only one markdown cell up here on the top, and then we have just about 1, 2, 3, 4, 5 code cells. So the first one I'm going to do is just going to pull out the key from my blob storage account from a secret store. That's a built-in feature in Databricks, and it is compatible with Azure Key Vault. So I set up Azure Key Vault, and I've pointed Databricks at it, and we've pulled in my key. And then what I'm going to do is I'm going to say, that's the container, Bluebadge HDI SC for storage container. That is the storage account. And what I want you to do is take the root of that container and mount it in the Databricks file system as /mnt/mypath. And with a little bit of rehearsal that's already happened, the system is telling us that, in fact, this folder is already mounted, so we're good to go. And now what we can do, notice we have a %SQL at the top of this cell, so that even though, if I can do a quick zoom in here, even though this is a Scala-based notebook, in this cell we can put Spark SQL. And what we're going to do is say, you know what, MNT MyPath, that's the root folder of the container. I know there's a JSON file in there with some radio airplay information. Let's create a physical table in the Spark SQL database around the data in that JSON file. And then let's do a good old select star and get the results back. And there it is. And as you'll see, and as this button might hint, you can take this tabular data and actually visualize it. But you'll see that in the next demo. In any case, let's go ahead and unmount this so that the next time we run that, we won't get a message that says, hey, you already mounted it. And then let's move on to our next demo. Now this one is more involved. This one is using Azure Data Lake storage, which allows us to store larger volumes of data. And what we're doing here is we're going to get the key for that account out of Azure Key Vault. And once we do that, this time we're not actually going to mount a volume. We're just going to set a configuration option with that key. And we're going to store the path to the container and to the storage account just in a string variable. We're also going to import a couple of namespaces that we need to run our code. So that's done. Now, this next block of code, I've already run it, and I have a flag set to false. So actually, it's going to skip all this. But what this did do was it read out a CSV file from a Databricks datasets virtual folder in the Databricks file system. So there's a folder in there called airlines, and within that there's a bunch of sequence files, a bunch of CSV files basically. But we can read in the content of all of those CSV files, even with that wildcard, and read it in as if it were one data set, and we can store it into this data frame. That's what we're doing. Then we are getting rid of some pretty bad column names like C0, C1, C2 and giving them meaningful names. Then we're going to create a view on that table. Then we're going to repartition it. We're going to say partition it into 200 pieces, but actually each set of 200 pieces, we're going to have that repeatedly for each year and each month for which we have data. Let's go ahead and run this. That will run very quickly because of all the stuff that was in this if statement. But we now have, look what we did. We partitioned it and we wrote it out as Parquet. So we kind of did two things at once here. And here is the path in the ADLS container that we wrote it to. So now that we did that, let's do really a file system command and see what is in that folder that we wrote out to. And because we have data for the years 2001 through 2008, we actually have a folder for each one of those years. And because we had partitioned this by year and month, we should within each one of these folders have 12 more folders, one for each of the 12 months of the year. So let's actually drill down on that and take a look at what we have in the folder that is specific to October of 2008. And aside from some flag files at the beginning, you'll notice that we have a bunch of Parquet sequence files. They end in .snappy.parquet. And the first one is all zeros. And if I scroll all the way down, you'll see that the last one is 199. And that's because we said we wanted to split this up into 200 pieces. So for each month within each year, we have actually 200 little Parquet sequence files. Now, because we have set it up that way, and now we're ready to get some work done here. So what we're going to do is read the Parquet version of that table back into a new data frame that we're going to call Gen 2. All right. Now, you're probably wondering how big that data frame is. And we could just do a count. We could do a %SQL and do a count against this view version of the data frame. So we create the data frame Gen 2, we create a temp table based on it called Gen 2, and we could do a select count star from Gen 2. Now I'm not going to run that because this actually, you can see from the last time I ran it, it took over 3.5 minutes to run. Now why is that? It's because we have a huge volume of data here. Ladies and gentlemen, this is a 9-digit number. This is over 500 million, billion with a B, also referred to as 1,000 million in certain countries. This is over 500 million rows worth of data. So hopefully you'll understand that when we say big data here, we mean it. Now there's a couple of queries that I've run already that I'm not going to rerun because they just take a little too long for a demo. This one, for example, took about 1 minute. Now, what did it do? It said that we want the count of flights in each day of each month specifically for the year 2006. Now, because we partitioned by year, that means we can go directly to the partition for 2006 and we can skip all the others. So that's going to give us some efficiency. We can go right into the folder specific to 2006. And because we sub-partitioned by month, that will help us optimize this group by and this order by. And then notice that the data would come back in a tabular form like this with month, day, and the number of flights. Month, day, number of flights. But we can easily visualize this as a stacked bar chart instead. And if you want to pick the particular chart type and what goes on each axis, just hit the plot options button and you should be good to go. All right, so what you're seeing here, each one of these different color bands is a different month within the year 2006, and then each bar going across the x-axis is a different day across the 12 months. That only took a minute, okay? Remember, we had over 500 million rows. Now, of course, we were only going after data in 1 out of 8 years, but that's fine. Now, this one doesn't get to take advantage of that partitioning so much because what we're saying is, I want you to give me the number of flights per carrier, per airline, where the airline's code starts with the letter A, and group it by the carrier. This one took 2.5 minutes to run, but it went across all 8 years and it really didn't get to take advantage of any of the partitioning. So that's impressive. These last two queries we can run live here. So I'm saying what we want to know is the total aggregate arrival delay minutes per month in the year 2002 for this particular airline. And I think AS translates to Alaska Airlines. So we're going to group by month, basically. It says year and month, but we already have a where clause on the year. So really, we're just grouping by month. And this should give us the aggregate delay time in minutes for that one airline per month in the year 2002. All right, and we got our answer back, and you can see, for example, that in March we had close to 1.2 million delay minutes in that 1 year. So that's a little shocking, but there it is. Our last query here, we're going to go ahead and say, I want you to show me the total number of flights in August of each of the 8 years that I have data for. So month is 8, so it's August. We're looking at Delta Airlines specifically. And then I want you to group by year. So we're getting a cross section of years. We're only looking at the month of August, but we're looking at it across a history of 8 years. And we should get that answer back shortly. Notice the previous query we did took just a little over 38 seconds. This one should be pretty close to the same. And yeah, that was 37.68, so very close. Notice the number of flights that Delta ran has basically gone down over the years. And that's the end of our first couple of demos. Let's go back to the slides. There's a lot more to cover. So let's keep going. Now we're going to talk about machine learning. And remember, I'm not assuming you know about machine learning, so let's just talk about the concepts. Machine learning is based on a pretty simple idea, which is that if you have a data set of historical data and you make notes about the patterns in the data and the relationships between a bunch of columns to one in particular that you're going to be interested in predicting, then you can build that model and come back later where you have data for all the input columns and the model will predict a value for the output. And we're going to go through a specific example or two, so if that sounds kind of abstract, that's all right. The thing you're trying to predict, by the way, is called the label. And all the input columns, all the things that kind of influence what you're going to predict, those are called features. And right away, you've already learned a bunch about machine learning because we've demystified some important vocabulary. So features and label really just mean inputs and predicted output. Once the model is built, as I said, bring it new data, put it through the model, and you will get predicted values for the label column. Let's look at this diagrammatically before we get into a code example. So imagine this very simple data set that has some retail data. We're looking at customers here, and we have some demographic information about those customers. We also have their annual spending level. Imagine all these customers are in our savings club. They've joined. They got a discount card for it, and we get to track their purchases because of it and their annual spending. Then imagine we get some new customers that just joined the spending club, the savings club, I should say. Well, for those folks, we won't know their annual spend, but we will know their demographics. So hopefully, what we can do is use some combination of most of these columns to predict the annual spend. And let's be specific about that. The annual spend is what we want to predict, and all the others are potentially inputs. Now, we already know a couple things, right? We probably know that something like the store type, whether it's in a mall or an outlet, maybe we want to discount that. The customer ID certainly is not going to be predictive of how much we spend. But age and recency of purchase may be, education level and marital status may be as well. So imagine we do some work on the data set. Imagine we put it into a data frame and we do some engineering inside of Spark and Databricks, and now we have it changed. So the customer ID is gone, the store type is gone, and the purchase recency has now been bucketed. Instead of having a particular date, we have a range of between 1 and 6 months, 6 to 12 months, or greater than a year. Likewise, for the age, instead of having a continuous value there, we have some brackets there as well. And for the annual spend, we've created brackets. So because of that, we're not going to try to predict a specific number. We're going to try and predict a bracket. So what we actually have converted this into is what's called a classification problem. All right, now that we have kind of shaped our data this way, those are going to be our features. That's going to be our label. And all of this, basically, we can consider training data. So we take our training data, and we take specifically the features and the label, and we feed it into a specific algorithm. And you'll see in our demo that we're going to use an algorithm called logistic regression, but there are lots and lots of algorithms. We say, these are our features, this is the label, chug through it, build me a model. And with one line of code, actually, you'll be able to invoke the training, and as a return value from that function, essentially, you will get a working machine learning model. Once you have that model, you can take some of the training data, because I kind of lied to you. The training data, we don't take all of it. We take, let's say, 75% of it. We build a model on that. The part that we held back, that 25% in my kind of hypothetical, that 25% of data, we can feed that into the model too. And we can play a trick on the model. We can tell the model, here are the features, go ahead and predict. We don't tell it that we actually know the answer already because this was historical data that we took. So we can have the model give us its prediction, and we can compare that against the actual that we know. So we're going to ask the model to predict, but we actually know the answer. And because of that, we can compare the model's predicted outputs with the actuals and get a sense for the accuracy of the model. And we can keep tweaking things, pick different algorithms or set different parameters for those algorithms until we get a model that has acceptable accuracy. And then once that's done, now we take our new feature data where we really don't know the label's value. We push that into the model. And by the way, we push in a data frame, we will get out another data frame, but that other data frame will have another column in it with the predicted values. All right, hopefully that makes sense. And in a second, we're actually going to go through that in a more concrete way. By the way, algorithms break down into different categories. As I mentioned, in this case and in the notebook case we're about to look at, it's a classification that we're predicting, but you can also do a regression operation where you're predicting a value. You can do clustering where you really aren't predicting anything. You just want to see how the training data breaks up into different groupings. And recommendations kind of make sense in the Netflix or the Amazon scenario where people who watch this might be interested in watching that. People who bought this product might be interested in that product. By the way, each algorithm has these tunable things called hyperparameters. And as you'll see, it makes sense to try and train the model, multiple versions of the model with different parameter values to optimize or tune those hyperparameters until you get the most accurate model. And the MLOps technology that we'll look at helps us manage and track all that, as you'll see. That's actually the demo after this one. But let's now get into the data science demo. And for that, we're going to go back to our notebooks, and we are going to go into this particular notebook. All right, once again, let's get our storage key out of Azure Key Vault. And then we're going to go ahead and we're going to mount that exact same storage container that we did in our first demo. And we're going to mount that to MNT MyPath just like we did in our first demo. So these first two cells in this notebook are actually identical to the first two cells in the very first one. Then what we're going to do is we're going to store in this variable here, we're going to store the full path to an input CSV file. And this is similar to what we looked at in the slides, but instead of trying to predict spending, we're going to predict income. Okay, and this is going to be the folder where a bunch of our output is going to go. Let's run this cell. Great. Let's import a couple of namespaces. We're going to import the namespaces for MLflow. That's going to allow us to do all the experiment tracking that we'll talk about in a moment or in the next demo. Now let's do a spark.read.csv and read in that input data. And we're going to specify that the first row is a header and that we want Spark or Databricks to infer the schema for us. Speaking of schema, let's take a look at the schema now that we have a data frame. So we have things like age and education level and occupation and relationship, capital gain, capital loss. And then what we've done with the income is we've just classified it to be whether it's over $50,000 or if it's 50,000 or less. And that's what we're going to try and predict in this case. By the way, this is a very typical machine learning problem in dataset. It's a public dataset. It's used over and over in lots of kind of educational scenarios. So this is not unique to Databricks in any way. This is almost like the hello world of machine learning. Now, realize we're not going to want to use all of these things as features to predict income. There's ethical issues. We don't want to predict income based on race, let's say. You know, we probably do want to predict income based on things like capital gain and capital loss. So let's take a look at this. Let's first of all create a view from that data frame. And then because we have the view, we can do a Spark SQL query around it so we can profile the data a little bit. This shows us how many people for each education level we have that make over 50K in our data set. So we have a lot for bachelor's and high school graduation, or high school graduate, I should say. And now what we're going to do is we're gonna split that data up. We're going to arbitrarily use this column and this sort of magic number value, and we're going to set aside a bunch of data for what's called validation, which in this demo we won't even bother with. The remaining data that's going to be in this data frame called train, we're going to want to further split that up so we have both training data and test data. You'll see how that works in a moment. Now what we're going to do is that first split, we're going to write the resulting data frames, we're going to write those out as Parquet files, because it's going to be faster to work with Parquet than it is with CSV. All right, and now that we have done that, we're going to read those things back in. So we wrote out Parquet data. Now we're going to create new data frames, or a new data frame based on the data from that Parquet output. And we're going to create a view against that. Now, remember what I said? We're going to kind of use 75% of the data for training and hold back 25 for testing. So that's what this is about. We say we want the training fraction to be 75%. The testing fraction will be the remainder. And we use this built-in function called random split, and we call it on our big data frame. And from this one data frame called train_df, we get two data frames back, one called train partition, one called test partition. We're going to go ahead and cache these and create views on both of them. And we have a little bit more kind of data prep to do. Most machine learning algorithms want all the feature data to be numerical. But for things like working class and marital status, we actually have strings. So there's a couple ways to handle that. One way is to say for each distinct value in that column, let me create an ID, and let me create a new column that has the numerical ID that corresponds to the string value. These string indexer objects will do that for us. So we're going to define a string indexer for each one of these string variables. And we're going to create a new column with the same name as the old one, but it will have a suffix of _ind. One exception to that, though, which is income bracket. The new name for that will be label, because it is the label, and we're going to want to document it as such. We're going to create a pipeline object based on those 7 string indexer objects. And then we're going to call the fit and transform method of the pipeline object, and that will give us a new training data frame and a new testing data frame that have the indexed columns in them, and we're going to go ahead and cache those in memory. And as soon as that runs, let's take a look at the new version of the schema. And it looks pretty much like the old one if we just look from the top down to about there. But then after that, notice we have our indexed columns, working class _ind, marital status _ind, and so forth. And for our income, it's not income bracket ind, it's label. Now that we've done that, we're ready to start doing our training. A little bit of prep in the first place, though. What we're going to do in this prep is we're going to say take all the columns that are our features, and these are them. So it's age and working class and final weight and education level, marital status, and so forth. And what we're going to do is we are going to create what's called a vector based on all those columns. And we're going to create an output column for that vector, and that's going to be called features. So that means we're going to have a column called features with all our feature data in it, and we're going to have a column called label with all our label data in it. By the way, what we're defining here, we're not going to run this code directly. This defines a function, train census income, and we'll be able to call this function multiple times. The reason we might want to do that is because there are going to be 2 hyperparameters for the algorithm we're using. We're using the logistic regression algorithm, And max iterations and reg param are two hyperparameters that we're going to want to tune. We're going to set those equal to some input values that are going to get passed into this function as parameters. Notice we call a function on MLflow called start run. So this is going to be an MLflow run, and you'll see some other calls to MLflow functions as we go through the code. Now that we have the logistic regression object, we have our feature assembler object. We store that in a pipeline. Then on the pipeline method, on the pipeline object, we call fit. And we pass in our data frame with our training data. And what we actually get back is a trained model. Once we have the trained model, we can call its transform method and pass in our test data frame. And we'll get back a new data frame that looks like this one, but has one extra column with the predicted values. Then we'll go ahead and create a view on that. We'll do a select star on it so that we can go ahead and look at the output. We will then create a view on that as well. And we're going to do things like log the parameter values. We're going to do things like log the input data set as an artifact. We're going to use a SQL query to see how many rows where the prediction was correct, where prediction and label are the same thing, and do that as a fraction over the number of total rows. And that'll give us a somewhat crude metric for accuracy, and we're going to log that metric. And then we're going to log the model as well. So let's run this, but nothing's going to happen because this just defines the function, right? But we can now call that function multiple times, which we're going to do in these next 3 cells. By the way, I guess I never told you how to run the cell. There is a UI method where you can just hit this play button and choose run cell. What I've been doing is hitting Control and Enter. You can do Control Enter or Shift Enter to run the cell using the keyboard. That's what I've been doing as we've been going through each of these cells, and I'm sorry for not mentioning that earlier. It's almost second nature to me, but that's not a good excuse. So remember, we're creating a data frame here called TMP predictions, or actually a table. We're creating a data frame called predictions, and we are, after the fact, we are going ahead and creating a temp table on it called TMP underscore predictions. So with that, we can have the SQL magic in this cell and do a select star. So these are the results from the third of these 3 runs. And if I put my cursor in here and I scroll all the way to the right, because this is our test data, we had actual values for the label, and we also have the prediction. And notice in each case, they're the same. 0 means that we're below 50K or equal to 50K, and 1 would mean that we're over 50K. I created this as a calculated column to say if this is equal to that, then true, and otherwise false. We also have a kind of confidence level, a probability that is identified right in this last column. And trust me, if we scroll down enough, you will start to find rows where the prediction wasn't right. In the next demo, we'll be able to take a look at the accuracy of each of the 3 runs that we just did. But for now, what I'm going to do is take the contents of this data frame minus this weird probability column, and I'm going to just write it out as a CSV file in the blob storage container. And that way, if I want to, I can download that and I can open it up in Excel and do some analytics and visualization there. And then I can just unmount my storage container from the Databricks file system. So guess what? We just did a soup to nuts creation of a machine learning model, and we did a whole bunch of predictions against it. Now, how do we judge how well those predictions went? Well, MLflow will help us do that. So MLflow lets us capture all of those iterative runs And as you saw in the code, it lets us log parameter values, metrics, assets, and the model itself. You create an experiment around it, and each notebook automatically gets its own experiment. So we have an experiment for that notebook. We have 3 separate runs within that experiment. And in just a moment, I'm going to take you back so we can look at the MLflow user interface and we can see which of those 3 runs was the most successful. Here is a summary of all those methods that we called: log param, metric, artifact, model. There is actually the ability to do auto logging, so you wouldn't even need those API calls. And there is a UI for looking at all the experiments and the individual runs within it. For any one of those models that we logged, we can actually put them into a model repository, and then we can do versioning, and we can even do promotion through dev, test, and production. And if we want to, we can deploy those models on a dedicated single node Spark cluster that will serve those models, put a REST API around them, and allow predictions to be run against those models from basically any environment that can do REST API calls. So let's take a look at the MLflow side of this. So in addition to having the MLflow API calls, there is a bit of a UI in here. And you see this, you see where it says experiment here, and there's a little 3 on it. Let's go ahead and click that and zoom out. And here are our 3 runs that we did. Now these are just summaries, but we can see that the accuracy is not bad. It ranges from 81% to 83%. If we click this View Experiment UI button, that will open up a new browser tab. And within that browser tab, we'll see all 3 of our runs listed. Let's just wait for that to come up. And then we can very easily do a scatter plot that compares the accuracy of each of those 3 runs. So there are the 3 runs. I could look at them one at a time, but what I'd rather do is select all of them and click the compare button. And now that I've done that, here's the scatter plot, and I can see this particular run, which used the values of 10 for max iterations and 0.01 for reg param in. That gave us 83% accuracy. So that's good to know. There's a couple of other visualizations we can look at here. By the way, there's a contour plot and a parallel coordinates plot. But that 83% accuracy run, we see it in this table here as well, right? And here is like a GUID for it, an ID for the run. If I click on that ID, we go into a details view for that run. Notice there's a button to reproduce it, and that's because we kind of logged all of these assets. Here is actually the, here are the log parameters. Here is the logged metric. We could have also put in some tags. And here's the model itself, and here's a CSV file that actually has the training data that we used to build the model. And that's pretty sweet. What's also kind of cool is if we click model, and unfortunately we're going to have a little bit of latency here because I brought up the CSV file that has quite a lot of data in it. But what you're able to do is you can click on the model here, and eventually you will see an option here that lets us deploy the model to the model repository. And then when you click this models button here on the left, that is that is where you can see all the models in the repository, and you can do things like promote them through dev to test to production, and even go ahead and deploy them. While we're waiting for the UI just to kind of come back, let's see if I can go into this tab. So here's another notebook. We're not going to run it, but notice that for certain machine learning frameworks, in this case a very popular one called scikit-learn, there is the ability to do what's called auto logging. And then all you have to do is call auto log and then call your start run, and then you don't need to you don't need manually through API calls to log the various parameters and assets. It will happen automatically for you. which is pretty nice. So let's just see if this came back. And it didn't. So what we're going to do is jump to the slides, talk about the next topic, and hopefully when this UI recovers a little bit, I'll be able to kind of show you the one piece that we weren't able to see live. So now we're going to talk about this thing called a data lake house. What does that actually mean? Well, there is an open source technology that Databricks created called Delta Lake. In fact, it used to be proprietary and was only available in Databricks, but now it's been open sourced, so you can use it with open source Apache Spark as well. Here's the thing you have to understand about big data and data lakes. For the most part, they are really geared to reading and not to writing. They tend to be read-only or append-only because the file systems are so-called immutable file systems where you can't really update the files. Now, what Delta Lake does is it gets around that. It accommodates inserts and updates and deletes by creating not just those initial Parquet files, because the Delta Lake format is based on Parquet, but it also creates files with just the sort of differences in subsequent operations. Another way for saying differences in the computer science world is delta, right? The delta between X and Y, and that's why it's called Delta Lake. So as you'll see, the way we handle this is that instead of rewriting existing Parquet files, we just create kind of supplemental ones. And by doing that, we can actually track a lot of state on the database and be able to go back to a previous state, keep the current state, and in fact, even all the updates, inserts, and deletes can happen within the context of actual ACID, highly consistent transactions. Pretty slick. It's not quite a data warehouse, let's be honest, but it does bring data warehouse-like capabilities to the data lake, and that's, of course, where the term data lakehouse comes from. So just, a few different API calls. You're going to see these in the demo that we're about to do, so I don't think I have to go over them in huge detail here. But notice that instead of saying format Parquet, we can say format Delta, and we have this ability to get a specific version of the data. That's kind of cool. We can see a history of everything that happened to it. We can compact, because eventually we're going to have lots and lots of files because we have these supplemental files. There's a vacuum command that will compact everything. And then a lot of this is available from Spark SQL as well. All right, so let's take a look at the demo. And we're going to go ahead and bring up this particular last notebook here. Now, there are a lot of cells in here. We don't really have time to go through every single one of them. What I'm going to do, we're in cell number 20 here. I am going to say run all above. That means we're going to run from the beginning of the notebook up until the cell right before this one. And while those are running, which will take a little while because it has to mount. Let's try that again. I'm sorry. Run all above. There we go. I think I must have hit run cell. Notice that this one says waiting to run. When it's done running, we'll know. And what we're going to do is pull in a public data set with a lot of retail sales information. There's a lot of data in there. We're going to pull out all the rows where there are null values. And when we're done doing that, we're going to have a data frame that has about 400,000 rows in it. We're going to take a random 25% of that data, and we're going to put it into this particular, or I should say, this particular data frame, retail sales data 1. So this now has 25% of the data, so about 100,000 rows. All the nulls have been removed, and we're going to write this out as a delta table. Before we do that, though, let me just mention this delta path with final slash. That points to a particular folder in our blob storage container. And as a matter of fact, I happen to have the Storage Explorer open to that very folder right here. let's do a refresh and just make sure. So right now we're looking at basically an empty folder. It has a folder within it for the Delta log files, but basically this is empty. After I run this line of code, it will save the Delta file to that folder, and so we should see a bunch of Parquet files. And even though we're not going to create a Spark SQL table against it right away, we can still do a SQL query against it just by referencing the path. So that's what's going to happen here. We're going to create the Delta table on disk, and we're going to select the first 3 rows. So those are our first 3 rows. And if we do a refresh over here, we now see all the Parquet data that resulted from this line of code over here. Now, we have a lot more work to do. First of all, we want to create a variable for the table. And then what we're going to want to do is take another 25% from the original data frame, or the originally cleaned data frame, and we're going to want to append that in as well. So now our data frame is going to grow, or a Delta table is going to grow from approximately 100,000 rows to approximately 200,000 rows. Then we're actually going to take that Delta table that's on disk and create a corresponding persisted Spark SQL table for it. And now we're going to do some other work. We're going to select one of the invoice numbers from that table. And for that invoice number, we're going to insert a new line item. Then we're going to update all existing line items and increment their quantity by 1,000. And then we're actually going to delete all those line items. We're just doing this so we can have a bunch of history generated and the ability to roll back to something more interesting. And let's go ahead and look at that history now. So we're able to say delta table.history.select, and we can specify certain columns from the history metadata. And look at what's happened here. This operation was our initial write. This was where we inserted the second 25% of data. And notice it gives us the number of rows, specifically 99,762. This was our insert, which shows up as just another write, but the number of output rows is just 1. And then our update, and then our delete. Let's come back over here, and because we did all those operations, we should see a bunch more of these Parquet files, because remember, we don't rewrite the old ones, we just create supplemental ones on top. Let's do a refresh there. Okay, we're up to basically 20 files. It says 22 cached items, but the first 2 relate to that child folder. So we have 20 Parquet files now. Let's go into that folder and notice that for each one of the 5 operations, 0 through 4, we have in the log folder, we have a JSON file and a CRC file pair. Okay, and you could go into those JSON files and actually interrogate their content if you wanted to. Now, I'm going to do a little bit more here. What I'm going to do is, in effect, 5 arbitrary updates. Why 5 arbitrary updates? Because that will bring the number of operations after the initial creation of the table. The number of subsequent operations will be 9. And then we're going to do this merge. Merges are pretty cool. You take one table and you merge it into another, and any rows in the first one that are new get inserted, and any ones that already existed get updated, and you do it all in one command. So that's pretty cool by itself, that we can do a merge in Spark because of the way Delta Lake works. But this will now be the 10th operation, okay? And 10 is a magic number in Delta, right? When we do the 10th operation, it will generate something called a checkpoint. And if we flip back over here and I refresh, you'll see that we have 10 JSON files, or actually 11 JSON files, 0 through 10, but we also have a checkpoint. And that's actually a Parquet file, and that Parquet file contains everything that happened in all 10 of these. so that later when we want to reassemble everything, if we want version 12, we don't have to start from 0. We can start from the checkpoint and then just go through the 2 JSON files subsequent to it, and we can reassemble things that way. And so we get some nice efficiencies out of Delta because of that. By the way, if we go back up to the parent folder, now we have a total of 40 Parquet files. And if we come over here, we could look at the history again, and here we should see 0 through 10, and indeed we do. And because that checkpoint file is a Parquet file, we could actually query it. That's what happens here. And we're seeing the internal contents of that checkpoint. And we could query it in a more structured way, though. For example, we could understand within it all the different times a file was added or deleted. And we could take all that information and we could insert it into this table called TBL checkpoint file. And then we could, if we wanted to, we could do a group by query to see the total number of file deletions and additions that took place. A couple more things and we're done here. We could do a time travel query. We could say, what's the current version? We actually know it's 10, but if we do a describe history, sales delta format, blah, 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 and we get the first row and the first column here, that will give us the current version. And then we can use this option version as of and get a count. That'll give us the number of rows in the current version of the database. We can do that again and hard code the version to 0 to get the number of rows in the original one. We can calculate the difference and we can output the difference, and we can see that in total we added 99,789 rows after that initial insert and then all the inserts and updates and deletes and the merge. All right, now we have a lot of files. We already saw that. Let's do a quick refresh just so we understand. So we've got a total of 40 files here, as we said before. And now what I'm going to do is I'm going to say vacuum that up. And I'm going to be a little bit severe and say I want you actually to roll back to the original version of the database by retaining 0 hours worth of history. And because we've done that vacuum, if we now come back over here and do a refresh, our 40 files go down to 14. And so you see we get some more efficiencies over there. The last thing we're going to do here is just set policy. And we're going to say, you know what, by default, just retain 7 days worth of logs and 7 days worth of deleted file information. And if we then do a describe extended on the table, we can see in the output that that policy information was in fact saved. An interval of 7 days for each of those things was saved. And at this point, we can just unmount the volume. And that actually finishes up our last demo. A couple more slides, and we'll be all set. Just to let you know that there is a new component inside of Databricks called Delta Engine. That's distinct from Delta Lake. Delta Engine is actually a rewrite of the Spark SQL engine in C++ for all the performance gains that you might expect would come with that. But it's more than that. You get a vectorized query engine. You get a cost-based optimizer. You get faster scan performance, faster parallel processing, adaptive query execution that can replan the queries on the fly. And again, by the way, all of this goes under the heading of the so-called Photon engine. So between the Photon engine and Delta Lake, you really do start to get warehouse-like capabilities in the lake. And because of that, something new, it just came out in preview about a day before the recording of this session, is a new component inside, a new UI component inside of Databricks called SQL Analytics. You will see in Databricks eventually one more button down here that lets you toggle between the Databricks workspace and the SQL Analytics workspace. SQL Analytics workspace gives you a query editor with built-in syntax completion. It gives you visualizations that are more sophisticated than the ones you get in the notebooks. You can create dashboards from those visualizations. You have auditable history. It's all based on a company and a product called Redash that Databricks acquired in June of 2020. And along with that, you also get the ability to deploy specialized clusters just for fielding those queries, so that those BI style queries can execute on your data lake without burdening the clusters that you have dedicated to things like data engineering and machine learning. So that's a little bit of an epilogue there. That brings us to the end of our time. It's been my pleasure to take you through all this material. I hope you enjoyed it. My name again has been Andrew Brust. Thank you very much, and enjoy the rest of the DPS conference. Thank you so much.
Because we've been this way from the start. Because the solution for one can be harnessed by others. Because clouds that compete can still connect. Red Hat, our code is open.